In this video, we're going to evaluate an integral using the definition of the definite integral and left or right endpoint approximations. Which of the following answer choices represents the limit definition of the definite integral below using a left endpoint Riemann sum? So they want us to take this integral and change it into a Riemann sum and pick the one that fits this integration. Well, if you remember from our previous section when we did left endpoint approximation, the left endpoint approximation is always a equals f of x0 times change of x plus f of x1 times change of x plus a bunch of stuff in the middle, and then we would have plus f of x n minus 1 times change of x. And this x of n minus 1, this comes from the Riemann sum here, or the summation here, where I is starting at 1. These sums always have I equal 1. So because I is equal to 1, that's how we get this, n minus 1. N is your ending point for your sum, so you plug that point in there, and that's how you get your ending x value. It's just saying it goes on forever. So what this gives you, so this is actually equal to then the sum from I equal 1, because if I plug in 1 in for n, I get x sub 0. So if I plug 1 in for n, I get x sub 0, which was our beginning piece. So from I equal 1 to n, we get f of xi minus 1 times change of x. So this is our Riemann sum for a left endpoint approximation. But we have to apply this to our current integral. So the first thing we're going to do is we're going to find what change of x is. Change of x is equal to b minus a over n. So b is 7 and a is negative 1 because this is our lower bound and our upper bound. So we're going to write this as 7 minus negative 1 over n, which gives you 8 over n. Now we don't know what n is, so change of x is just going to represent this 8 over n part. So then what we're going to do is we're going to say, all right, once we have this 8 over n part, we need to figure out what is this xi minus 1 piece. So, and how does it relate in here? So we have x of I minus 1 is really equal to x sub 0 plus I minus 1 times change of x. Now this is kind of an interesting piece that we put here. So xi minus 1, the reason we have xi minus 1 is equal to x sub 0 plus I minus 1 times change of x is change of x is what we always add to each of our x values. And if you remember that from our previous section, we were adding change of x because that was our width. And so this is how we got the different widths of our triangles. Well, I is always going to start at 1. So if I starts at 1, we get 1 minus 1, which is x sub 0. So that better equal x sub 0 here. Well, that's why we put this I minus 1 piece here, because this would be 1 minus 1, which is 0, times change of x. So this starts us at x sub 0. And then when I is 2, we get x2 minus 1, which would be 1, equals x sub 0 plus 2 minus 1, which would be 1, times change of x. Well, that is what x1 is equal to. If you remember from our previous sections, x1 was always equal to x sub 0 plus change of x. So this just is an expression representing what xi minus 1 is equal to. Well, we can use this expression then and say that that is really equal to x sub 0 in our case is negative 1 because that's our lower bound. So we're going to say that that's negative 1 plus, and then we're going to have I minus 1, and we know what change of x is, that's 8 over n. So then we can go ahead and distribute that out. So I'm just going to write that as equal to, that would be, let's distribute that to each term, so we have minus 1 plus 8I over n minus 8 over n, which if I make this negative n over n, so I have negative n over n plus 8I over n minus 8 over n, I end up with 8I, if I rearrange that top a little bit, 8I minus n minus 8 all over n. And so that is what xi minus 1 is. Now, remember, I'm trying to figure out what f of x minus 1 is. I want to know this piece here, f of x minus 1. So we're going to go ahead and, because this is our very important piece that we're going to use to figure out which one of these works. So I found xi minus 1 to be this. I now need to find what f of xi minus 1 is. Where our function is 9x squared. So if I say f of xi minus 1, that means I'm going to take this xi minus 1 and plug it in for x. So I get 9 times 8I minus n minus 8 over n. So this is what f of xi is. So then I can write that my Riemann sum would be n, or the summation from I equal 1 to n, of, if I replace f of xi minus 1 with what I have written here, which would be 9 8I minus n minus 8 over n, and then also replace change of x with 8 over n, I can now multiply some of this stuff together and maybe do a little factoring. So if and I forgot the square. So that's 9, this should have been 9x squared. So let's go ahead and square the inside and then multiply all this together. This would equal n from I equal 1, the sum from I equal 1 to n. When I square the inside, I end up with 9 on top times 8I minus n minus 8 squared, and that would be times 8 as well because of this 8 there, and that's all over n. This would be squaring the n would be n squared times n, that'd be n cubed. Now I can factor some stuff out here. I can factor the 8 times 9 piece, which would be 72, and the n cubed. So I would have 72 over n cubed, and then I'd have the summation from I equal 1 to n of 8I minus n minus 8 squared. Well, you can see that we've got our Riemann sum then. That would be the second sum right here. And I did forget one little thing. I need to write that this would be the limit as n approaches infinity. So I did forget limit as n approaches infinity, because n can go on forever.